Alright, so let's try doing videos a little bit different here. I'll try writing instead of the smartboard. So this video is going to cover Lewis dot structures. It's going to come in 3 parts. We'll do Lewis dot structures in general for individual atoms, then put them together into some simple molecules, and then we'll do ionic Lewis dot structures, and finally show you an additional method of determining Lewis dot structures that I call NOS. So Lewis dot structures, just in general, can be used to represent covalent or ionic bonds, as I mentioned, and they only use valence electrons. So we don't really care how many electrons there are in the whole structure, we only care about the valence. And the valence are the s and p electrons on the outermost level of the atom. So those are the only ones that we care about. An easy way to remember those are to look at where the atom is placed on the periodic table. For example, nitrogen here. He is on the second row, so he has 2 rings worth of electrons, if you think about the Bohr model, and we're just going to count backwards. This is the p block. This is the s block. So for nitrogen, counting backwards, he has 1, 2, 3, 4, 5 valence electrons on that outermost ring. So just a quick step-by-step on how in general we do this process. Again, this is for individual atoms only. So first thing we need to do is determine the number of valence electrons for that particular atom. So let's say we were doing something like carbon. First thing I need to know is how many valence electrons does carbon have. Well, let's see. S and P on the outermost ring, second row, 2 rings. Outermost ring, 2 in the P, 2 in the S, for a grand total of 4 valence electrons. The E for valence electrons. Next thing we need to do is to write the symbol of the element we're talking about. So carbon, that's the one we're going to do. And then we're going to place the electrons as dots around the symbol as if it were a 4-sided box. So pretend there are 4 sides to a box around this carbon, and we're going to place 1 electron, 1 dot, on each side before we start doubling up. So 4 electrons that we need to place. It does not matter where you start, whether I start up here on the side, on the bottom, it doesn't matter so long as you are consistent. I like to start on the top, so I'm going to put 1 electron there. Here's 2, here's 3, here's 4. That's all my electrons placed, so I have 1 on each side, 4 unpaired electrons for carbon. And that's it. To try something where we actually have to go around more than once, let's do something like the element fluorine. Not the ion fluoride, but the element fluorine. So here he is, second row again. So let's count. We got 1, 2, 3, 4, 5 electrons in the P, 2 electrons in the S. 5 plus 2 is a grand total of 7 valence electrons that I need to place. Again, we pretend we have 4 sides to a box. I'm going to start on the top again with my first electron, second, third, fourth. So I've only placed 4 electrons, but I need to go up to 7. So onward we continue. Here's 5, 6, 7. 7 valence electrons placed, so I have 3 pairs here and 1 unpaired electron. Again, if you started on a different side, that does not matter. So if we had started over here, that would have put my lone electron on the bottom. Both of these structures are completely valid. You can do either. The only exception to this going around rule is an instance where we have electrons only in an s orbital. So only from that s block. For example, something like calcium. If we look at calcium on our periodic table, he only has 2 electrons in the s block. So outermost ring, that would be the 4th ring here. 1 electron in the s, 2 electron in the s. If you remember your electron configuration, those 2 electrons are together. If you draw the spin diagram, they are still together. So on your dot structure, since we only have electrons in the s, they are, again, together. And that's only for elements that have electrons exclusively in an s orbital. Quickly, let's mention ions. If we were to do the Lewis dot structure for an ion, let's say perhaps fluoride, so F negative. That negative sign tells me I have picked up an extra electron. Fluorine had 7 valence electrons, if you remember from before. So fluoride is going to have 1 more. 7 plus 1 is 8. So 1, 2, 3, 4, 5, 6, 7, and 8. Fluoride, in fact, has a full octet of electrons. If we were to do a positive, here's where things get a little tricky. If we were talking about sodium ion, for example, sodium plus 1, sodium. Regular old sodium has 1 valence electron. When I go to the ion form, I have lost this 1 electron. So this is the form that you will usually see for sodium. We use those brackets whenever we have a charge. Occasionally, you will see all 8 valence electrons that are on the next level. So if you think about sodium, if he loses that 1 electron, that gives him a configuration just like neon, who has 8 valence electrons. So occasionally you will see them drawn with all 8 electrons from that 1 level behind, but this is the one that you will typically see with no valence electrons, since we have given up the 1 that we had. So I hope that clears up any misunderstandings about Lewis dot structures for individual atoms. If you watch the next video, we will go over Lewis dot structures for ionic compounds. It won't take but a moment because it is quite brief. See you next video.